Maria. Hello. Today is Friday, February 19th, and this is ECE 637, Digital Image Processing 1. And today we're going to pick up on the discrete time Fourier discrete space Fourier transform. But I do want to cover a couple things because I guess next week on Friday, can somebody double check that, is the exam? Okay. So the question is, how does one study for the exam? So the answer to that is that, hold on, the first thing you have to do is learn how to open the web browser. This computer is really slow. Okay. Browsers, I guess. Google. Excuse me?
Looks like they already started recording.
Oh, yes, they did. Yes, I'm sorry. Google. Hold on. Oh, I'm in Google. What am I doing? Okay. 6:30. I used to be able to just type Bouman, but no more. Okay, and then I go here and okay. So if you want to study for exams, the best predictor of the future is the past. Okay, so you go over here to previous courses. Okay, and here we have all the previous courses. Now, last year was a little bit funky because we have a solution to exam 2, but not. Hold on, what did we do? Oh, okay, this was a little funky because it was the pandemic. The first exam was normal, and then I guess the second exam started getting weird. But here, this was like a normal exam. Now, I'm going to use Gradescope, so it's a little different, and I've been trying out some different things. But the bottom line is this, and there's a solution here, right? It usually says key, or often says key, and here's solutions. Okay, now, so, but here's the thing. You can go to previous offerings. Oh, what's going on? Oh, because this is a previous offering. So I can go to 19. That's more typical. So I go to exams. And there's an exam. Okay, and then there's a solution, which is often scanned. And there are some exams that have no solution. I don't guarantee that every exam has solutions. But most of the exams have solutions. Okay. So now if you have to guess, if you want to, so students will ask me, well, what's a typical exam like? What's the exam going to be like? That's what they ask, okay? So now, what would be the common sense answer to that question? It's going to be a lot like the previous exam, right? So what's a good way to prepare for the exam? You guys are all, graduate students, PhD candidates in electrical, in one of the most challenging fields. So, given this, what's the best way to prepare for the exam? Go over the old exams, right? Like, do the old exam problems, right? Obviously. So, it's good to try to do them without looking at the solutions first. But if you can't figure it out, look at the solutions, okay? So, so that's the most obvious thing to do, right? Study the notes, go over all the exam solutions. So you might be wanting to work on that this weekend since the exam's next Friday. The other thing is that I'm going to use Gradescope. How many people here have used Gradescope? Okay, so I might give a fake Gradescope exam. Maybe I'll try to do it like over the weekend or something. So first of all, here's the thing. Gradescope is a piece of software for taking exams, okay? So you have to, and for that software, you have to upload either a PDF or a JPEG of your exam solutions, okay? So you can prepare that any way you choose, but one sort of obvious thing to do is to write the solutions out on a piece of paper and then to scan them. You can easily scan them with a cell phone, right? Cell phone, like I have software, I have Dropbox. I pay for Dropbox, but you can get Dropbox for free, and it has a feature in it which is a document scan. But I think there's lots of document scanning software, right? So just get some kind of document scanning software for your cell phone. If your cell phone's not good enough, because then you can buy a scanner, I guess. Okay, that's your responsibility. I had a student whining and moaning yesterday for not this class, another class. Yeah, okay. It's your responsibility to figure out how to do that. And do it efficiently, because if you're screwing around with this thing, scanning documents, then you're wasting time. I'm going to give you extra time on the exam, but it's going to be a fixed amount of time. It'll be, say, an hour and a half or something like that, okay? Maybe I'll give you more. I don't know. But it'll start at 9 a.m. on Friday. It'll start at 9 a.m. Eastern New York time, okay? So I guess this is Eastern Standard Time right now, right? So it'll be 9 a.m. Eastern Standard Time. Gradescope, the way Gradescope works is that you can't actually enter the solutions until that time. And then here's the other thing. So let's say it's 2 hours, okay? So 9, 10, 11. Let's say it's 1 hour. So at 11, at 9, at 9:59, you better have your answer in, because at 11 o'clock, you cannot upload the answer anymore, right? That's it. You're hosed. That's it, okay? So you make sure you have to have your solutions uploaded, okay? Like common sense, right? Don't wait to the last moment to upload it, right? You often put things like that. What I'll do is upload the answer, and then if I change my mind, I can re-upload a better answer or something like that. But make sure something's uploaded, okay? And when you scan the document, don't scan the document so that it displays like this, okay? If I get a lot of these and it really puts me in a bad mood, I might take off points, okay? Because I can't rotate the image on the screen. The software doesn't allow me to do that. So I have to scan the document. I have to grade it like this, okay? Don't do that. And if the image looks like really, really dark and you can't read it, scan it again. Just, common sense. It doesn't have to be beautiful, but make sure it's readable and it's uploaded properly and the thing's not rotated sideways, okay? And in order to do that, practice it in advance. So I'll give you a fake exam. I'll ask you, like, your favorite color or something like that, okay? And you can write it out and you can test your system for scanning documents. And make sure you test it, excuse me, make sure you test it on the same, systems that you're going to use. Don't say, well, I tried it on this computer, but then I actually took the exam on that computer. Well, obviously, test it on the computer you're going to use, right? I'm just reviewing basic things. I think the main thing is just that students don't think about it and then they wait to the last minute. So don't wait to the last minute, okay? You're going to send an email, right, to all the students, reminding them that they need to prepare to use Gradescope. Now, when I do the Gradescope, I haven't quite decided yet, but I might use a different system because Gradescope actually displays the exam questions and then you put in the answers. But maybe what I'll do this time, it's a new technique, is what I'll do is I'll write up the exam as a separate PDF, which will probably be available on Brightspace because I can time the, I guess I could email it. I'll either email it or I'll send it on Brightspace or I'll do both, okay? Okay, so then what will happen is you'll have the exam and then you'll answer the exam questions on Gradescope, so that the exam will be formatted as a PDF, right? And then you can keep the exam after but the grade scope, at the end of the allotted time, it stops, and you cannot upload the answer. So what happens is this. I always get students who email me and say, I didn't get my answers uploaded in time. Okay. I can't grade the exams if the answers aren't uploaded because it's extremely difficult to work around the Gradescope environment. Okay, I kind of have to. It's not even really possible for me to upload your exam once it's not been uploaded. So, if you do have some kind of problem or some meltdown thing, obviously contact me. Okay, but please practice. I think once you get used to it, it's not that hard. But the problem is a lot of students are doing it for the first time. Okay, is there any questions about that? And you can actually, I don't know if you actually need a Gradescope account. I don't think, you guys took Gradescope exams, right? Okay, so do you actually get a Gradescope account, or does it just show up as an email and you click on it and it takes you to Gradescope?
I was through the university, like I'm enrolled in the class that I'm taking the exam for. Yeah.
Yeah.
So like, I think it's university affiliated.
Okay, but it comes as an because from my point of view, I don't actually see exactly how it works. Like,
You can either
You've got to sign
have
up
it
for
send
free.
an email, or if you just log into Gradescope with your Purdue
Okay,
information,
okay.
as long as you set up the class
Okay.
and to it.
So everybody should log in Gradescope with their Purdue career account, just to make sure that login works. And I'm pretty sure, but not positive, and that theoretically you can go to Grades. Theoretically Gradescope is linked up with Brightspace, but you can actually access it completely separately. So you can go to Gradescope, log in, and I'm pretty sure you can log in with your Purdue career account. Right, that's what happens. Okay, so make sure that's all working and tested. All right. And any other questions about preparing for exams? And the exam will cover, well, what it covers will depend upon how far we get this week. But it will be cover everything up to and including, say, wherever we stop. It might be like sampling or FIR filters or something. Okay, we'll see for sure. Okay, any other questions? All right, good. Okay, good. Now, I guess, well, maybe maybe should, I don't know. Yeah, I guess I'll do it like this. I'll do it with the, that's okay, I'm throwing everybody off. Okay, so we were talking about the 2D, the 2D discrete space Fourier transform, and it results in a periodic transform and in that case, the transform goes from any period of 2 pi. So typically people will talk about it going from minus pi to pi because that's more intuitive. You can also talk about it going from 0 to 2 pi, but that's a little less intuitive, I think. So then there are transform properties for the 2D discrete space Fourier transform, and they're essentially the same properties as you have in 1D. So I say they're inherited from the 1D case. They're fairly obvious. It's linear. Conjugation of the function results in conjugate reversal in the frequency domain. This is not real directly intuitive, but it relates to other properties. This property basically relates to the fact that real valued functions are got to be conjugate symmetric. Then shifting in time results in linear phase modulation. Linear phase modulation in time corresponds to shifting in frequency. So this would be modulation like you'd use for FM radio, but now it becomes 2D modulation. Convolution in space corresponds to multiplication in frequency. So this would be like a 2D linear space invariant filter. And multiplication in space represents convolution frequency. So this would be like if you do windowing. So in one of the labs for the power spectral density estimation, you had to use a window. in order to reduce the size of the side lobes. So so this is that, okay? And then I do want to talk about windowing. I guess we'll talk about that in a little bit. Yeah, but there's some some properties of the discrete space Fourier transform that are sort of specific to the 2D nature of it, so they don't have an analog in the time case. If a function's separable, we say a function's separable if it's formed by the product. So the 2D function, if the 2D function is formed by the product of two 1D functions, right? So we talked about separability for the continuous space case, and the same thing happens for the discrete space case. Then the Fourier transforms are going to be the product of the two Fourier transforms, okay? The 2D Fourier transform is the product of the two 1D Fourier transforms, okay? And there's no scaling or rotation property. Why? Because you really can't scale a discrete time function. If you stretch it, now the sample points are not going to fall in the correct grid. You can scale a continuous time or a continuous space function, but not a discrete space one. Which you also can't rotate it because again the points won't fall on a grid anymore. So and that leads to a lot of methods that because in some practical sense you need to be able to scale discrete time signals or discrete space signals. Like for instance, let's say you have an image on a TV on a display and you want to rotate it, and so you have to, and so you need a theory for handling that, and we'll talk about that later. But the Fourier property doesn't exist in the same sense. Now there's this thing called a 2D Z transform. Actually, did we talk about 1D Z transform? Oh no, there's a 1D Z transform. And let's first talk about the 1D Z transform. So if you look at the 1D discrete time Fourier transform, this is what it looks like. So it's the sum over n of x of n times e to the j omega n. Well, if you're writing these things out, you find yourself writing e to the j omega n a lot. So if you think about it, if you take z equal to e to the j omega, then e to the minus j omega n is just equal to z to the minus n, right? So if I make a substitution, I get that x of z is equal to the sum over n, from minus infinity to infinity, of x of n times z to the minus n, right? So it's kind of interesting. So the point here is that, and this thing here is called a Z transform. So you'd say, well, there's no difference between the Z transform and the discrete time Fourier transform. Well, that's not exactly true, because there is a difference, because what happens is that Z here may not be equal to e to the j omega. It may be that z is some general complex number. So the way to think about it is that in some sense the z transform is a little more general, and you have the real and you have the imaginary, and the z transform. So the discrete time Fourier transform is the z transform evaluated on the unit circle. Because e to the j omega is the unit circle, right? The unit circle is e to the j omega. Everybody knows that, and that this is omega. It's the angle of the point. So, okay. So what ends up happening is that the z transform doesn't never necessarily exist for all values of z. If the magnitude of z is large, then e to the minus z will have a magnitude which decays as n gets large. So if x is a causal signal, so the sum only exists for positive values of n, then z will decay. And so the bottom line is that this sum may exist in some cases and not exist in others. So the z transform won't necessarily exist for all values of z. Okay? Okay, so understanding when it exists is an issue. So, okay, so this is the z transform. It turns out that you can prove that the inverse z transform has this following relationship. You need to, in order to interpret this, you need to know what a contour integral is. So this is a contour integral of the complex plane around the ROC is the region of convergence. Okay, and the same thing happens in 2D for the 2D z transform. So, okay, this is what I just already told you, that if the discrete time Fourier transform exists, then it's equal to the z transform evaluated on the unit circle. And if the 2D discrete space Fourier transform exists, then it's equal to the 2D z transform evaluated on the unit circle. Now, the z transform doesn't always exist. Like, for example, let's say I have x of n is equal to e to the, is equal to a to the n, where a is equal to 2. Okay? Then the discrete time Fourier transform would be x of e to the j omega is equal to the sum from n equals minus infinity to infinity of xn, oh, I'm getting sloppy here, times e to the j omega n. So that's equal to the sum from n equals minus infinity to infinity of 2 to the n times e to the j omega n. Oh, e to the minus. Is that what you said? Okay. So that's equal to the sum over n of 2 times e to the minus j omega to the n. Now the problem is, this is not absolutely summable. I mean, it's just really, it's difficult. It's not really possible to assign any meaningful value to this sum because the magnitude is growing, right? So, for example, if omega is 0, so that would mean like e to the j 0 is equal to the sum over n of 2 to the n. Well, obviously, that sum is equal to infinity, right? So it's not convergent. So the discrete time Fourier transform doesn't exist for this function. But the z transform does, because I could take z, if I make the magnitude of z small enough, then it'll counterbalance the effect of the magnitude of a. So what will happen is that the region of convergence, x of z, right, the region of convergence, this is real, this is imaginary. So the region of convergence, as long as the magnitude of z is, so this is 1/2. As long as the magnitude of z is less than 1/2, this thing will be the region of convergence. So in that case, the unit circle is not contained inside the region of convergence. So that's unit circle. So the moral of the story is that, okay, so the way it goes is like this. There's a few things to know here with Z transforms. Okay, so for Z transforms, okay, that's the discrete time Fourier transform exists. Okay, if and only if. Okay, x of n is stable, and that's true if and only if the region of convergence contains the unit circle. Okay, now for a causal, signal, the region of convergence always lies inside the poles. So, so what you may have heard is that a signal is that a signal is stable if and only if its poles are inside the unit circle. That's I'm sorry. Yeah, so the region of convergence lies outside the poles. No, it's inside. I've got this mixed up. Okay, so this is for causal signals. What did I do wrong? Did I flip something?
For causal, region of convergence is outside the bottom.
Yeah, so why did I think? Yeah, it's outside. Oh, because it's e to the minus z. That's why. Right. Oh, I did this backwards. Shoot. I'm so sorry. I did this backwards. The region of convergence here, I drew that figure incorrectly. Let me redraw that figure. I shouldn't bend it. I have to be careful. So x of n is equal to 2 to the n. Okay. This is real and this is imaginary. And z here, the region of convergence is given by the magnitude of z greater than 2, not less than 1/2, because you're taking it to the you're multiplying e to the minus z. I've made this mistake before in the past. So this is the region of convergence. And this is the unit circle. I flipped them. Okay. So the result is the same. That again, the here the DTF, discrete time Fourier transform, does not exist because the region of convergence does not contain region of convergence does not contain unit circle. That's the general result. The more specific thing you may have heard is that you hear that the signal is causal if the poles are inside the unit circle. And that's true for causal signals. For causal signals, so the x is stable if and only if poles lie inside unit circle. There's a really bad joke about this. I feel like I need to tell it. So a plane is flying from Warsaw, and all the people in it, they move to the they move to the left-hand side of the plane, and the plane crashes. They go, why? They go, well, because it's they move to the right-hand side of the plane because they say because it's only stable if the poles are on the left-hand plane. Okay, sorry. I'm sure you could do a better job at that joke. Okay. Okay. So, and actually, this is unit circle, and the reason it's the left-hand side of the plane is because if you do the continuous time case, which is the Laplace transform, then it maps to the left-hand side of the plane. But for a causal signal, it's stable if and only if the poles are inside the unit circle, because the region of convergence always falls outside the poles. In this case, there's a pole at right here, I think. Okay. Anyway, that was a quick review of Z transforms. So the thing with Z transforms is that the advantage of a Z transform is you can take a Z transform of a signal like x to the n. So what is the Z transform? Actually, I should just work it out since I've been talking about it. Is equal to 2 to the n. So it's x of z is equal to the sum over n, 2 to the n times z to the minus n, right? So this is equal to sum over n of 2 times z to the minus 1 to the n, right? Now, the sum, times, let's make it times u of n. So this is n equals 0 to infinity. So this thing here, the sum of a to the n from n equals 0 to infinity is equal to what? It's 1 over 1 minus a. You should memorize that. You can prove that pretty easily, right? The way you do that is you factor out a, and you'll get a sum. You can solve that. You get kind of a recursion relationship, and you can solve for this. Okay. Anyway, so that means that x of z is equal to 1 over 1 minus 2z inverse. For this is the signal. So this is what's called a pole at 2, because at 2 this goes to infinity. For z equal to 2, this goes to infinity. So that's the Z transform. Now, yeah, there was a point I wanted to make here. There was another point I wanted to make. Z transform. Okay, so this is a causal signal, and that's the Z transform, right? I know there was some other point I wanted to make, but I've lost track of what it was. Oh, shoot. Sorry. There was some point I wanted to make. Oh, I know what the point I wanted to make. Okay, the point is I wanted to make is that this thing has no... so x of n, x of z, okay, x of n equals 2 to the n times u of n. This is has x of z equals 1 over 1 minus z I'm sorry, 2 times z inverse exists, but x of e to the j omega does not exist. So the point is that you can take z transforms of things that you can't take DTFTs of. Sometimes you can take the z transform, but you can't take the DTFT. And in particular, for unstable signals, you can't take the discrete time Fourier transform, but you can take the z transform. So z transforms tend to be much more popular in control theory, because in control problems, you need to understand when a system's stable and when it's not. And the discrete time Fourier transform is not an adequate tool for that, because when the system's unstable, you can't take its transform anyway. So, but in signal processing, I would say maybe this is just my opinion. The Z transform is a little less popular, because the disadvantage of the Z transform is it only has analytical form. For the Fourier transform, you can actually, evaluate it on a computer, because it takes on you can evaluate e to the j omega on the real line for omega between 0 and 2 pi, whereas z is in the complex plane. That's not realistic that you can evaluate z. The z transform is always used in its analytical form. So the Fourier transform is more useful as a computational tool, but the z transform is more useful to analyze stability of theoretical analytical models for systems. Okay? All right. Any questions about that? The sampling is our next topic. Okay, sampling. So sampling is really important because it represents the fundamental way in which you convert signals from continuous time to discrete time and back. So the idea of a sampling system is that you have a G of t as a continuous time system, and then you just evaluate the G of t at a particular discrete point, and we'll usually assume that the points are uniformly spaced with spacing uppercase t, and n is an integer here, okay? So this is a linear system because the definition of linearity is that not just that if you scale g by a continuous value, well, two things. If you scale g by a continuous value, the output gets scaled by a continuous value. That's clearly true. But if you add two functions together to form the input, then the output is the sum of the sample values of the two inputs. So this is a linear system, but it's not time invariant. So we learned about linear time invariant systems or linear space invariant systems, but for a linear space invariant or time invariant system, you need the input and output to both either be continuous or both be discrete. If you mix it up, then that's not true, because I can make continuous positional variations of the input in time, and the output will change in a sort of a complicated way, right? I can't. I'm constrained to have discrete shifts of the output. So then what's the input-output relationship? Well, this is a simple representation of the input and output relationship. You'd say, well, that's very simple. Why can't we just leave it at that? Well, it turns out that you can get a lot more insight into the problem if you look at this relationship in the frequency domain. Actually, the relationship in the frequency domain is substantially more complicated, but it gives you a lot more insight. So if you do that, it turns out this is the relationship. You'd say, like, gee, you must be a masochist. Why would you take something so simple like that and express it in this complicated way? Well, because it gives you a lot more insight. Here's the intuition. The intuition is that, okay, when you sample a signal in frequency, okay, so you have a signal, and this is in frequency. So let's say this is F. This is frequency 0. Okay. And we have some kind of thing. Okay. And the sampling rate is Fs over 2. And this is minus Fs over 2. Okay, so this is g of t. This is g of f. It's the Fourier transform of the signal in continuous time. Then when we sample it, what happens is that we get a new signal. Okay. And this axis I'll call omega, because by convention, I'm sticking to the letter omega to use as the variable for frequency in discrete time. So this is 0 frequency. So 0 frequency, what will end up happening then, that this point, Fs over 2 will correspond to minus pi, and this will be pi. And then this signal will end up mapping like this. So it looks the same. Now, the one thing that does change is the amplitude. So this amplitude, if this is 1, this will go to 1 over t. I'll talk about that in just a minute. Okay. So, but the key idea to remember is that, and then this thing here is going to be s of e to the j omega. S of g e to the j omega, that's the frequency transform of the output. So this frequency transform of the input is g of f. The frequency transform of the output is s of e to the j omega. Okay? So in the frequency domain, the important things to remember is 0 frequency, and this is the continuous time frequency, and this is the discrete time frequency. 0 goes to 0. Half the sampling frequency goes to pi, and minus half the sampling frequency goes to minus pi. Remember, pi is the highest frequency you can ever have, because when you have a frequency of pi, I kind of did this before, I think. If you have e to the j pi n, that's equal to e to the, oh, I wrote one thing and said another. Just say that again. Okay. So if you have omega equals pi, e to the j pi n is equal to e to the j pi to the n. That's equal to minus 1 to the n. And minus 1 to the n looks like plus 1 minus 1, plus 1 minus 1, plus 1 minus 1, like that. You can't change any faster than that. So if I raise the frequency above this, the frequency is actually going to go down, we're going to see, instead of up. So this is the highest frequency, and you may actually know, or at least heard, that the highest frequency that you can support with the sampling system is half the sampling rate. So put another way, if you have a signal, let's say an audio signal goes to 3 kilohertz, you have to sample at twice the maximum frequency. That's sort of like, I don't know. It's like one of those things you just, like, if you wake up during the middle of the night, you just blurt it out. That it's drilled into your brain as a signal processor. You have to sample at twice the highest frequency. It's called the Nyquist rate. So for instance, audio CDs support frequencies between 0 and 20 hertz, 20 kilohertz, I'm sorry, 20 kilohertz. So you have to sample at least 40 kilohertz. Now, in order for practical reasons, they sample a little higher, okay? I can't remember the exact number for audio CDs. It's something like 42 kilohertz. What is it? 44.1. Okay, yeah. So they leave a little bit of slop in there because it makes it easier to process the signal. But the minimum is 40 kilohertz. If you sample below that, we're going to see you have problems, okay? So why do you have problems? Everybody understands this part, right? Now here's the problem. This can't be correct. I got to be lying to you, okay? Why? Because I told you that this is a discrete time Fourier transform. It's got to be periodic with period 2 pi, and this is not periodic with period 2 pi, right? So how do we fix that? Well, that's where this sum comes in. See, it looks kind of ugly. All this part here, the omega minus the divided by 2 pi t, that just does all this scaling. But now you got this sum with a shifting thing going on. So what is that intuitively? What that is that there's a thing here, it goes to 2 pi, and it's 3 pi, okay, and then it's like this. So you periodically extend it. Now the problem is, if the sampling frequency, see here, the maximum frequency, we'll call that FC for cutoff. That's the maximum frequency. If half the sampling frequency is larger than the maximum frequency, or put another way, if the sampling frequency is more than twice the highest frequency, then these don't overlap. But if that constraint is not met, if the sampling frequency is too low, or if the frequencies contained in the signal go up too high, then these are going to overlap. When they overlap, that's called aliasing. And the reason it's called aliasing is because if you sample a signal, if you sample this signal, I think I did this last time, e to the j pi plus omega n, that's equal to e to the j omega minus pi, because that's the same thing as adding 2 pi n. So this has the interpretation of, this is pi frequency and this is minus pi, that as you pass over this boundary, so this is the frequency, as you move this way, you actually come back here. It reminds me, in fact, we'll see this later, that there used to be a game. I'm told it was one of the first video games. I believe that, too. Has anybody ever played the game Asteroids? How many people have played the game Asteroids? There are no classic video fans? You have played it. Yeah, okay, I know it. Okay, because, okay, yeah, for sure. Okay, so Asteroids was one of the very first video games, and I'll tell you why. So they have this, it's a great game. I think you can buy like imprinted versions with the original digital code or something like that. And you have a little spaceship, which is a triangle, okay? And then you have asteroids, which look like this. They look like sort of funny polygon-y things, okay? And then if you hit the asteroid, you blow up, and that's bad, okay? But you can also fire little things out of here, and you can blow the asteroids up, okay? So here's the thing. And you also have like a rocket you can fire. Oh, how many people saw the Mars lander land? Oh, that was pretty cool, actually. My daughter's boyfriend worked on the helicopter, okay? And they had to test it in a vacuum. They had to pump down the vacuum, okay? So it hasn't flown yet, though, so he's not in the clear yet, but Marcel. Oh, I'm running out of time. So what happens is that when you fly over here, you come out here, okay? Okay? And sometimes there's an asteroid, and you crash unexpectedly. So the thing is, this is wraparound. And that's what happens. Wraparound, that's what happens here. These wrap around. Pi and minus pi are attached. And you just go from one to the other. And that's called aliasing because basically that frequency is posing under an alias. Okay? It's like if I was a criminal and I used a different name. Right? It's an alias. That's where the name comes from. So that's what happens. We'll go over that, finish it up next time. Thanks a lot. See you on Monday. Bye.